Looks like we can start officially. Welcome back, everyone. We're about to finish off our week 4, so we're getting across the 75% mark, which is pretty exciting. And congratulations also getting on through the very first exam for the course. I tend to get these graded as soon as possible. In the best situation, I should have it done on Friday. But if it takes a little bit longer to grade, I did assign 2 exams this week. It'll extend into the weekend. And if you get your grade returned on Sunday, that means I was very behind. But Sunday is going to be my final cutoff. I'll make sure somehow, some way, even if I have to put in late hours, to always get those grades done before the next week starts. We're going to finish off section 2.5, getting through the very first chapter. Then after we get through that set, we'll be moving into the next exciting chapter on logic, starting in 3.2. 3.1 is a chapter opener. You ought to read those to get a feel for the landscape. But the section, just like in chapter 2, that we start officially will be 3.2. Well, that's a pretty brief amount of announcements. Any questions at all, folks, before we get started? Okay, well, let's jump in. We last left off dealing with functions, talking about domain, codomain, and then doing some tricky problems on what is the domain and range for particular sets of functions. There was a ask for the class if people want more detail on how I got the equation that described the range of one particular function, being a plane in R3. So if you're curious about the step-by-step procedure there, take a look into these notes for the optional reading. Also, this is connecting back to the very first homework set. We were looking into the fourth root of -9. The standard answer I think the author was expecting on this one was just undefined. But if you're curious on how to compute them as complex values, this would be the other side of the optional reading. And Jake says, just to make sure, we're allowed to take the exam up until Thursday, right? Yeah, that's absolutely correct. The exam is going to be open for each one of these exams that I assign from Monday, if you wanted to take it early, to Thursday on the latest cutoff. And that extends to even people on the in-person section as well. Just out of the sake of fairness, we'll always have it expected to be on, say, a Tuesday. But if something works out just better, maybe that's a busy day, and you want to schedule it in Idaho Falls Testing Center on a different day, then that always works out for even the in-person section. Oh, let me scroll back
So I
there.
have a quick question.
Yeah,
Um, so considering the textbook said that it should be undefined, are we to assume for the purposes of this class that the square root of any negative number is undefined and we're not using the imaginary domain?
yeah, that's true.
Okay.
So any even root pretty much of a negative number whatsoever, we'll consider and treat as undefined. I mean, it's kind of unfortunate to be a bigger landscape if we got into the complex numbers, but then that's really kind of its own course in and of itself. So yeah, you can always treat those as, I mean, they're defined in a certain sense, but for our purpose, they'll be undefined. Other questions so far? Okay, well, let's move into the last part of section 2.5. We cut off this section before going into the exam at a pretty good spot, I would say. Here's 2 definitions about functions that we're going to come back to over and over again in this course. Well, maybe not necessarily over and over again, but we'll be revisiting these definitions later on in prior chapters, in the next chapters, rather. And these are concepts that come up in lots of different settings in math courses as well. So we'll be looking into the concept of an onto function, as well as the concept of a one-to-one function. Well, to start off, let's look through the definition. We'll say a function that maps from a domain A to a codomain B will be called onto if for every element B that's coming out of the codomain, there exists at least one element A in the range such that F maps that domain element to B. So we can always solve this equation for some particular choice of A. So that's what's meant by being onto. And if you like the fancier word surjective, this comes from the French language. That's a synonym in this class. So an informal way of saying it is an onto function is just one for which the codomain is equal to exactly the range. We'll look at a few scenarios down below here, but a graph is a good way to look into this just from functions we're very familiar with. If we say write out a function, say f of x equals, how about x squared? And we further define f in this particular way. You have to be specific about domain and codomain before we answer the question of is it onto or not. If we say f maps from R2, excuse me, not R2, R into R, then in this example, this is not an onto mapping. Because if I can find a number b, say, let it be -1, here it is, such that f at -1, f at x equals -1 can never be solved for this function. So we can write f at, these colors are getting a little bit of a distraction. Let me just go back to black. F of x equals -1 has no solution. Again, that's getting back to the concept we're restricted to real valued functions. We're not working in the complex plane. So since we found a value for which there's no x resulting in that output, that particular function f is not onto. But if you change the landscape of how you define this function, a function has a lot of moving parts in its definition. It has a domain, it has to have a codomain, it has to have a way of defining it. Change any of those elements, and you've possibly changed this conclusion right here. So let's take a really fast screenshot of this so far. I'll park it up here, just the initial thoughts before thinking of the definition. And let's say we changed it just a little bit and say f still has the same domain R, but the codomain on this one is going to be 0, infinity. It's now an onto function, and this little counterexample to onto doesn't work any longer. The number we would be picking for b in the definition above has to be somewhere, say 0, that would be one value, but f of 0 would equal 0 for this particular function, or maybe it's somewhere up here, say a 4, or maybe even a 3, any positive number whatsoever. We can find the right x value. So that's a 3 there. Put in square root of 3, and that would be the input that results in that particular output of a 3. So this time, it is onto. So the domain, the codomain are critical elements in making this kind of definition. We have an onto function in this case, but in the prior case with R being the entire codomain, it was not onto. But that's what this part is trying to say right here. Your function is onto if the range is all positive numbers, including 0, equals the codomain. We fix the codomain to be non-negative numbers, so now it's onto. Any questions at all, folks, with that quick tour of onto? Okay, let me put it up above in case you want to take another look at those. That's kind of huge though. So there's a non-onto version. Here's the onto version. And this is what the typical exercises are going to look like in this section. We'll look at some functions involving the modulus operator, some other functions we're familiar with, some trig functions, thinking about onto. And these ones are pretty fast to check for onto. We want to determine if f from the domain 0, 1, 2, 3 to the same set as a codomain 0 through 3 integers is onto. All we have to do is 4 function valuations at the maximum. So this one just becomes a bit of a review topic on modulus itself. We can compute starting with f of 0. F of 0 is not too bad, except it's a -1 again. We'll get -2 mod 4. I find for these, it's easier for me to just crawl through the formula on this. This goes, let's cite it up above. N mod k is n minus k times the floor of n divided by k. So I'll think in those terms to compute this. This will be -2 minus 4 times the floor of negative 2/4. This is negative 0.5, so the floor of that would be a negative 1 altogether. We have a negative 4 minus 4 times negative 1 coming from the floor. So that's just a glorified 4 minus 2 altogether. And we hit one value in the codomain, 2. If this is an onto function, we have to hit every single value. So let's see what happens next. Any questions at all, folks, with the evaluation side so far? Okay, continuing on, let's move to the next element, f at 1. We're plugging 1 here, so this is just a 1 minus 2. So now it's negative 1 mod 4. So this is negative 1 minus 4 times the floor of negative 1/4. The floor of both of these values is the same, so that's kind of convenient in this particular setting. This is negative 0.25, so the floor is still a negative 1. So this is negative 1 minus 4 times negative 1 for a value of 3 altogether. So now we've hit that element, and so far so good. Looks like it could be an onto function. We're moving on to the 2 and the 3, so f at 2. That's going to be 4 minus 2, so that'll just become a 2 mod 4. And 2 mod 4 would be exactly 2. In this case, this is probably where I wouldn't necessarily use this formula any longer. I would revert to the interpretation that modulus is the remainder upon division by 4. 4 doesn't go into 2, so the remainder is 2 itself. So that's a fast way to think about it. There's no harm done if you ran it through this definition here. You'll get the same exact value. But notice we have a problem. There's been a kind of collision. F has mapped both 0 to 2 and 2 to 2, and it has a finite domain with just 4 elements. There's no way I'm going to be able to hit 0 and 1 with just the last value 3, because it's a bona fide function. F at 3 can't be both 0 and 1 at the same time. It's going to be one or the other. So we can stop right here and just say it's not onto. But for the sake of really visualizing this, let's do the full evaluation. One more can't hurt. F at 3, that's 3 squared, so 9 minus 2. That becomes a 7 mod 4. And 7 mod 4 is 3, and that's another collision. We never hit 0 and 1 whatsoever, and so we can conclude right here, therefore, F is not onto, because we can focus on either element. I'll just focus on the 0. F of x equals 0 has no solution. There is no x value whatsoever that you could pick in this set, and we've checked them all. That's going to map to 0, and same problem on the 1. We just focused on the 0 here in our conclusion. Well, any questions, folks, on that onto check here? Okay, onto one-to-one comes up in lots of different kinds of contexts. This will come up in, say, a linear algebra course. It'll come up in an abstract algebra course. I believe it might be a concept that comes up in Calculus 3, but I would have to think about that. That's something I need to check out to be really sure about. Sophia says, what do you mean by onto? By onto, what we mean is every element that we map here, if it is onto, would have an output that includes both of these values. So because we never actually hit the 0 nor the 1, that's what made it not onto. And looking at tracking it through the definition again, it says the function mapping A to B is onto if for every element in B, and this would be the set B down below in that definition, there exists at least one element A from the domain. This would be our set A in that definition, such that at this equation, f of A equals B can be solved. We focused on the 0 when we found that it didn't matter which x value you picked, 0, 1, 2, or 3. There's one equation we cannot solve. There's no value you can plug in here whatsoever. to output the 0. So that would mean not onto. But if we did have, say, a 0, 1, 2, 3, all the elements got hit by a domain element, we would have said it is onto. Does that make sense with that question there? Yeah, absolutely. Thanks for asking about it. These, again, are pretty abstract and tricky kind of problems. So there's lots of ways you want to try to think about the definition. In its pure logical definition form, through working a simple example like this is a great way to kind of internalize it. But also, for any kind of definition that involves a function, always try to relate it back to something you're familiar with. Any kind of pre-calculus algebra topic, say these kinds of graphs, are a great way to think about onto. So this one was not onto because there's no way to get f of x equals a -1. But this one was onto because we changed the range to be, the codomain to be non-negative integers. And now on this one, range was equal to codomain. So those are going to be a couple pictures we'll take a look at again when we look into one-to-one. But for the sake of more practice on onto, this is not one of those concepts where you want to just spend 5 minutes on. We'll practice out a couple more. Any other questions at the moment? Okay. So next one on the list, we're going from R to R. The function is defined by f of x equals sine x. We were wondering, is this one an onto function? Well, here's one where we could say, think about the trig function geometrically in terms of a graph. The graph would look about like this. Let me try again with the sine function. I'm thinking cosine. Sine starts at 0. Sine of 0 outputs a 0. When you get over to pi over 2, reaches a maximum value of 1, but then it starts to descend again. When you hit pi, sine at pi goes to 0. At 3 pi over 2, it's descended all the way down to a -1. Then finally at 2 pi, we're back to 0 again. So this is not by any means the complete graph of the sine wave, but it's a periodic function. If we replicate this one piece from the period 0 to 2 pi, we have the entire graph. But notice the values that we actually take. It goes from -1 to +1. In other words, if we say the codomain is R, we can absolutely find an element B in that codomain R such that this equation is not true whatsoever. So let's work through this carefully. Let's say set B equals 2 or -2, any number that's beyond 1 or -1 going down. Then f of x equals 2 would then imply sine x equals 2. But that's a problem. No matter what x value you take, you never take a height at 2. You're always restricted between -1 and +1. This has no solution x in the set R, which was the domain. So if you can't solve that, that means it's not onto. There's particular values inside this entire codomain, the real numbers, for which no x maps to that value. 2 was just one particular counterexample. You could have picked 5, square root of 2, any of those kind of values would work. But the conclusion this time is, again, therefore, f is not onto. We're going to have one onto example, I promise. I think it's the next one. But any questions thinking about the sine wave problem? Okay, let's turn into, still thinking in terms of trigonometry. Let's look at the one with the cosine wave. Notice the big change though. Our domain is still all real numbers. That makes sense for any kind of sine cosine function. But the codomain has been severely restricted between -1, +1. And that's kind of sensible because that's the actual range of both the sine and the cosine function. So we expect this one to be fully onto. Questions you might have is, how much detail do you need to show on this kind of problem? We haven't really gotten to the section on proofs just yet in chapter 4. So if you give me an informal statement of every element between -1 to +1 has an element in R such that cosine of that right element gives you back the number, just a few full words, that would be okay with me. If you decide to answer this kind of question, say by outputting a graph, sine x, and whether you drew the graph on paper or just analyzed it, you could tell me that it goes between -1, if I can land there. Oh, there we go. It goes from -1 all the way up to +1 in all of the output values. I swear it gets to +1. That's just really hard to hit today for some reason. You're gonna have to trust me on this one. It hits +1. Desmos is just not playing along. So because the outputs go from -1 to +1, I guess it works that way better. This would be an onto function. So if you say in ordinary words, that'd be completely fine. If you're thinking about tracking the definition as carefully as possible, here's what the work would look like for this one. So here's our definition. Let's follow our nose on this. It's going to be onto if every element in B is this set from -1 to 1, we can find an element A in this set, that's the entire real number line, such that f of A equals B. So let's start by just saying let B be in the set from -1 to +1. Next thing we can do is, let's say set x equals cosine inverse of B, where x is in the set. I want to go from 0 to pi because that's the actual domain of the cosine inverse function that I'm defining. So I'm grabbing an element that I think is going to work. That's going to be my x, or the a if you prefer to call it that way. If we write, then f of x, that means we have to go back to the definition of f of x. This will be cosine, throw in what x was by another substitution, cosine inverse of b. And then by properties of functions, the cosine function and the cosine inverse function undo one another. It's a clean cancellation, and you get the output b. The key elements of the argument that we just wrote down was, I never said what b was. It is 100% fully arbitrary. Any element, whether it's -1, -0.999998, or up to +1, any number whatsoever works with this particular x we chose. So we have proved that this is definitely an onto function. And this is giving us really also a preview of what's coming in chapter 4 when we look into proof techniques, and chapter 5 when we specialize into proof by induction. But again, I'm not going to be super picky on how you answer these questions. We're just getting started thinking this way. So if you resort to ordinary graphical analysis, say what you see on page or draw it on paper, that'll be a fine solution as well. Just think in terms of the onto here to guide your reasoning. Well, one thing you should also do on paper before I forget is, it's okay to have a nice argument, but never forget the conclusion. That's super important, like I was about to forget. The conclusion, let me just emphasize it because I nearly forgot it, is f is onto. Because no matter what particular value you take out of the codomain from -1 to +1, we can find a value. It was x equals cosine inverse b, solving that equation, mapping into the b value in the codomain. Well, any last questions at all, folks? Thinking about onto functions?
So, um, I, on the topic of trigonometry, I was wondering about things like arctan, and this might be out of scope, but are it's it's defined almost everywhere except for I think pi over 2 and all repeats of that. So do we have ways of expressing periodic uh, disjoints? I can't think of the right word.
So you're thinking in terms of onto, maybe the function is the arctan function. That's a great one to think about. Are we thinking arctan or just tangent itself is the question on this one.
It's one of them. I can't remember precisely, but it's how it has vertical asymptotes every
Gotcha.
yeah.
Well, this is going to be a difficult set to write. So yeah, let's think about this one while we're on the topic. Definitely not out of scope. That's a good example. So if we're saying arctangent, and it needs a value, this is kind of the nice one. The domain is all real numbers. It caps out at pi over 2, doesn't actually hit the value, so there's a horizontal asymptote. Similarly, at negative pi over 2. So it's not on 2 if your codomain is R, but if your codomain goes like this, let me get back to the tool. Here we go. If we say f is mapping from R to negative pi over 2 to pi over 2, this function is on 2. And so this was kind of the nice case. But I think the spirit of the question is more tangent itself. That one's a little bit touchier to think about.
Yeah, I was thinking about tangent.
Yeah, so let's look into that one. So how would we even write the domain of tangent? That's a pretty good question in and of itself. First, let's put on tangent. And like you said, it's undefined at infinitely many different locations. So here's tangent x function. Looks kind of overwhelming when you graph this, especially if you zoom in a lot. Loads and loads of problems. But notice the range is all real numbers on this. So if we were trying to express a problem involving tangent itself, we probably would have to do something along these lines. We'll say f goes from R, but that's not quite right because remember it had all those problems. So we have to do R set minus a set that goes X such that X is a real number and X equals any multiple of pi over 2, as we were saying. So let's call that K times pi over 2. So these are all the problematic values we're seeing here, any multiple of pi over 2 whatsoever. If you take those out, where K is an element of integer, any integer whatsoever, that's the domain. So kind of a nasty domain on this one. It'll map to R itself kind of nicely. There we go. So if we're really, really careful with how we write out the domain, we can say that this one is on 2. And the reason being is even if we restrict to just one region between negative pi over 2 and positive pi over 2, the vertical asymptotes are giving us all possible positive values whatsoever, no matter what large number you pick, or even 0, we can find an input to map to it, and same for large negative numbers. So this one would be an onto function. Let's put the graph on there just for the sake of emphasizing it. But again, the difficult part of that one is to really make this a precise statement altogether. You have to say exactly what your domain is, and it gets kind of finicky with the trig functions. Really, sine and cosine are the only nice ones, and the other 4 have all sorts of problems like these. But does that make sense with that question there?
Yes, thank you.
Yeah, absolutely. Other questions so far about onto? Let's see. Sorry, say that again.
I'm thinking it would be K times pi minus pi.
Oh, gotcha.
We're skipping every pi, right?
Yeah, thanks for mentioning that. So pi over halves just gets us started, and then it's going to be pi over half is the first one, and then the period is pi, so k times pi. So we can go plus k times pi. Does that make sense with that revision there? So here we'd go pi over 2 being the first problem point, undefined as expected, then take an integer, say plus 5 times pi, still undefined, no matter what that integer is now, -8 now, still undefined. So yeah, it looks like that's the right format. Thanks for fixing that there. I got a little bit just any multiple of pi over 2 takes you here, but you're defined. So that still wasn't quite the right set. So from R set minus all of that stuff with that revision there, this important revision. Thanks for mentioning that. That's a good eye on that one. We now have the right domain and we can make sense of this function. It's on2 as defined this way. You know, if we change the domain to something weird like that, the problem is that could work as a domain. But if you take out pi, any multiple pi over 2, you put a hole right there where you can't actually map to, and then it's no longer on2. You're listing all the values. 0 is not part of the range set any longer with the way I wrote that set prior. So it becomes just really critical how you write these out to make sure your conclusion is finally sound, on2 versus not on2. But other questions or comments so far? Okay, so that's the landscape of on2. Thanks for the follow-up questions about it and the careful eye on that strange domain that was written down. For the next one, topic we'll tackle is one-to-one. There's a lot of interesting different equivalent ways, logically equivalent ways of saying one-to-one. I have two different versions down here. We'll start with one-to-one being defined in this way. A function is now one-to-one if for any element B in the codomain, there is at most one element A in the domain that satisfies this equation. A maps to B. The at most is very, very critical here. It's possible you found a B from the domain for which this has no solution. That means it's not on2, but that doesn't invalidate one-to-one whatsoever. The function can still absolutely be one-to-one, even if this has no solution for a particular value B. What we're saying is, once you found one solution, there can be no others that map to B whatsoever. So that would give us one-to-one. And the author admits these definitions are tricky. One-to-one, I think, is a little bit trickier than on2 in certain senses. And so here's an alternate way to define this. We can say a function mapping the same set A to the same set B, say the same function, will be one-to-one if for any element A1 in the domain and any element A2 in the domain that are distinct, they're not the same values. Let me redefine my highlighting to kind of match up with the at most. If I find two different distinct domain elements and then look at the outputs, there is no way they're equal if the function is one-to-one. There's no collisions is an informal way of saying this. There's no way to map to the same value with multiple inputs. So this is the essence of one-to-one, either way we look at it. And again, if you're a fan of the French language, the way one-to-one is often said in a lot of textbooks, even plenty of English textbooks, injective is the word for one-to-one. Kind of like that word, it sounds cool. It kind of gives you a visual that you're injecting a domain element into exactly one output, but no others. First thing we'll do is get a visual on this relating to what we know. So pre-calculus kind of functions, things we're familiar with seeing. But any questions at the moment with just the definition? Okay, we'll put our graphs up here when we take a look into them. Let me see if I can organize this just slightly better so it doesn't look like a mess in the notes when you come back to it. All right, I want a one-to-one example. And I want a not one-to-one example. Let's bring on the graphing calculator. So first, for a nice one-to-one function, it'd be anything along these lines. F of x equals, how about a x? I mean, that does it. This is one-to-one. If you take, say, an output of 1, there is only one possible way to get to there. Your input was 1. So you map here, going back to the 1. There's no other way to do this. And this could be our example. It's a simple function, but it does the job. This is one-to-one. Geez, let me fix the size of that. So here's our one-to-one example. Sorry for the jittering around while we get things the right size. And I kind of flipped that. I don't know how that happens. Hang on. There we go. That looks a little bit more normal. So here's our one-to-one example, right side up this time. Not one-to-one is easy to cause. All you need to do is put in any even exponent. This one is not one-to-one. And here's the trouble. If you're thinking about, say, a domain element, just any one that's easy to see on the graph, let's go with the 2. There's a collision in the sense that there's 2 ways to map to 2 for this function. You take the value square root 2. Here it is. And it will map to 2. Well, this one's negative square root 2. If you take, say, positive square root 2 over here, it will map to 2 as well. So since f at negative root 2 equals f at root 2, they're both equal to 2, and negative root 2 is certainly not equal to root 2. They're opposites. This function is not one-to-one. You could call it a 2-to-1 function if you preferred. Let me get just a better screenshot. But this is our mental image whenever we're thinking of something that's not one-to-one. And let me see if I can fix that without flipping it. There we go. Oh, geez, hang on. Microsoft is just not playing along too nicely today. I'll clean that up later so you don't have to watch me struggle with Microsoft Word. But any questions at all, folks, with the 2 quick examples of one-to-one and not one-to-one? Okay, I like this picture here along with this definition. Somehow just in my head, this is the way I like to think about it. If you ever have 2 elements that are not equal, but the function values match, that means you are absolutely not one-to-one. But if you always grab distinct elements and they always map to different values, that's the not equals, then you're in the one-to-one case. So the fact that we got equality here is why we said not one-to-one for that particular example. We'll look into a couple scenarios just like we did before. Looks like a couple mod functions and a 3rd degree polynomial, and that will round up our one-to-one discussion. So nothing too crazy with trigonometry on this one, it looks like. Here this time, looks like 2 mod functions we're looking into from a finite domain to another finite domain. Notice this domain has size 4 in cardinality, 4 elements. The codomain has size 7 in its cardinality. So even though the question is about one-to-one, here's an important thought. There is no way it's on 2. Because my range is only going to have 4 elements, and that's size 8 altogether, miscounted. But the question is about one-to-one. And a good way to just determine if this is going to work out, are all the outputs not equal, is just start computing like we did on our on2 example. So this is kind of the relaxing side of the notes. Let's do some evaluations. Throwing in a 0 here is going to give us 0 mod 8, which outputs a 0. Now we're looking for collisions hitting the same output more than once. So we go down to the next domain element, f at 1. Plug a 1 here, that's just 1 minus 1, so that's 0 mod 8 again. And that comes out as 0 again. At this stage, we should just stop because we have two different inputs. We have an A1 and an A2. They are absolutely not the same. 0 is not equal to 1. And yet, their outputs matched. We can say this implies f of 0 was in fact equal to f of 1. Not equals means 1 to 1. So equality here, the first time we see it, means not 1 to 1. And then that's where the problem ends, right at that stage. Any questions at all, folks, on example 4?
So does this imply that if our codomain is uh, not the same size as our domain, it cannot be one-to-one?
Sort of. It kind of just depends on the sizes.
Okay.
So that's a really good comment on that. Let me put down something on the notes. You could say something along these lines. If you're going from finite domains, that's where the funny stuff happens. If you go from A to B, so here's domain to codomain, and let's look into the cardinality. Let's say the cardinality of the set B itself is smaller than the cardinality of the set A, strictly smaller. Kind of the opposite of this situation. Say I'm mapping from maybe 5 elements into exactly 1. No way is it going to be 1-to-1, right? If there is only 1 element in the codomain, every value maps to 1. It's not 1-to-1 any longer. So this is the direction where it's always going to tell you, as a foregone conclusion, not 1-to-1. We would have to have that relationship on the sizes of domains. And they would also have to be finite size. So let's say less than infinity as well. So if this happens, this implies f is not 1-to-1. So that's a really good side thought. Thanks for mentioning that. Does that make sense with the conclusion here?
Yes.
Awesome. And yeah, these ones didn't quite go in that direction. I made the codomain just really large, so we couldn't go to that kind of statement, but that would have been a fun problem. For example, I'll fix this in a moment, but if it was this set, then you're done. It's not 1-to-1. No way, no possibility for that. But if it's 1, 2, 3, well, now it depends. We have to do the mappings, see what we get to see if anything overlaps, if there's any collisions in the output. And I made it just kind of a wide landscape on this one, 0 through 7 for the integers. Other questions at the moment?
So if our codomain is smaller than our domain, it might not be one-to-one, but it could be onto.
Yeah, exactly. So it would definitely not be 1-to-1, but onto is an absolute possibility. And this is the reverse idea on this one. If it's finite domain and codomain, but your codomain is larger, automatically cannot be onto. You know, that's not a bad one to just put down on the notes as well, just as a kind of adjoining topic. If F maps from A to B, and the size of the set B is larger than the size of the set A, and I want these to be finite sets. So I'm going to say it's less than infinity because if they're both of infinite size, just about anything can happen. But this will imply f is not onto. There's just no possibility because the domain values are smaller set than the codomain. We can't map to everything in there. There's too much stuff. And that's what was going on in this example over here. Let's put these in the little boxes as the side thoughts. Other questions at the moment? Okay, let's try out to whatever is going to go on with this one right here. We're mapping from the set 0, 1, 2, 3 into the codomain 0 through 7, just like before. So the setup is the same, but the function definition is different now. So our strategy is just see what happens with some values. Take f of 0, that's going to turn into 0 mod 8 once again, which is 0. Then throw in a 1. This will be a 1 minus 2. So this one is -1 mod 8. So I'm going to cite the definition on this one, the nice function. This is -1 minus 8 times the floor of -1/8. And same issue as we done before. That one is really just -1 itself, the floor of -1/8. So this is -1 minus 8 times -1. So that's an 8 minus 1 for an output of 7. We can't stop yet. So far, all of our outputs are distinct. It could be 1-to-1. So we keep going. If there's no overlaps whatsoever, we'll just say it is 1-to-1. So let's see what happens when we map 2. F at 2 is going to give us 8 minus 4. So this is 4 mod 8. Let me double check that. 8 minus 4. Okay, I think we've got a 4 there. 4 mod 8, that just outputs a 4. And still, there's no collisions on our output values. So last value to map, f at 3. F at 3, let me do this one carefully. I don't want to mess up the arithmetic. That's going to give us 3 squared, so 27 minus 6 mod 8. So this is going to be 21 mod 8. Now 8 times 2 is 16, times 3 is 24, exceeding this. So we go back to the 16. The remainder will be 5. And all outputs are distinct. Because we have all distinct outputs, we can conclude, therefore, f is 1, 2, 1. We were never able to get to that equality right there. We picked distinct elements, then f at those distinct elements are never equal. That's an impossible equation for all these outputs. So this is what a 1-to-1 function would look like. Certainly it's not on 2. It didn't hit every single element. 2 was never mapped into, but all the outputs are distinct. Let's just put that as a side thought. Since all outputs are distinct. And there's a lot of concepts you could connect to this. If you're dealing with finite sets, then 1-to-1 is essentially saying the size of the domain equals the size of the range, not the codomain, but the size of the range. If those are equal sizes, then you've got 1-to-1. If the size of the domain and codomain, one or the other, are infinite sets, then the analysis is a little bit harder. But these are great problems just to start thinking about 1-to-1. We'll look into one more. Here, now we're going into infinite size sets, so we can't just look at the size of the domain, codomain, and make a decision. This one just depends. But any questions at all, folks? Finalizing any of those prior examples? Okay, this one is not too bad to get through, but it's another one of those questions, just like on the onto analysis, where the level of detail could be a good amount on this when you think about how to run this through. I'm going to accept multiple arguments for this particular one, like I was talking about with onto. If you cite a graph and you observe that you're looking at a 1-to-1 function on that graph, that would suffice. But for the sake of the preview of what we're getting into when we're looking into logic chapter 3 and our proof techniques in chapter 4, I want to give an argument that's just kind of a preview of what we're doing later on. We want to present an argument that it doesn't matter who shows up to see your argument, no matter how hard they're going to try to heckle you, they cannot refute your logic. And here's how I would start. I want to see if we can work through any versions of these definitions. And let's start by saying, let f at A1 be equal to f at A2. So if I start right here, I'm looking for the possibility that it's not one-to-one. But if this equation will only hold if I have distinct elements, A1 and A2, I have a sound argument for it turns out it is one-to-one. Let's read through this definition again to just kind of get a warm up on how our argument should go. One-to-one says, if we have two elements, A1, A2, that are distinct, then f at A1 is not equal to f at A2. You can turn that logic around. It pretty much just looks like this in the logic. If A1 is not equal to A2, then f at A1 is not equal to f at A2. So that's the essence of the alternative definition. It's a little bit more terse. It's an if-then statement. But we're going to see in chapter 3, you can turn if-then statements around just to suit the purpose of how you're going to work the algebra on paper. If I turn this statement around, it would look like this. If f of A1 equals f of A2, then A1 must be equal to A2. So either way we look into this is a one-to-one statement as well. It feels like a different kind of sentence, but essentially what I started over here is negate this, assume they're equal, then negate that statement, assume they're equal here, and this is one-to-one at the same time. Later on, we're going to call going from here to here, taking the contra positive, which is a really cool logical technique that you can do with any if-then statement. What you do is you start with this. If you're going into the contrapositive, again, negate it. So the negation of not equals is equals. And the old hypothesis here becomes your conclusion in the contrapositive, but you negate it as well. The negation of A1 is not A2 is that A1 is equal to A2. So we're going to work the logic using the contrapositive statement. I think on paper, algebraically, that's just the easiest way to say it. So I started with the assumption f of A1 equals f of A2. That statement's right here. Then we'll follow our nose with the algebra. We can do the function evaluation. That just means 2A1 cubed equals, let me start over, 2A1 cubed minus 4. That's f at A1, evaluate here, equals 2A2 cubed minus 4. That's f of A2, just plugging A2 here. Now we can work with this algebraically, add 4 to both sides. 2A1 cubed equals 2A2 cubed. Divide by 2 on the next step. A1 cubed equals A2 cubed. And then finally, you could just take the cube root of both sides of this equation right as it stands. Cube root of both sides gives you the conclusion, A1 equals A2. This wouldn't have worked if that was to the power 4, you will notice. That's power 4, and I have A1 power 4 equals A2 to the power 4. Taking the fourth root would give us plus or minus in our equation down below. That's not good for us. We want just direct equality here, not multiple values. But because we landed exactly at A1 equals A2, we can make a strong conclusion. Therefore, f is 1 to 1. And these are the kind of arguments that we're going to try to give later on. Again, when we're further on in chapter 3, we'll look into onto again, 1 to 1 again, and see how to write these airtight kind of arguments. Occasionally changing around the definitions to make it more just helpful for the algebra that we write out, taking a contrapositive like we see here. But any questions whatsoever, folks, with the conclusion on 1 to 1? Okay, well, if we put both of these both of these technical definitions together onto 1 to 1, surjective, injective, we get the so-called bijection. So bijections plays an extremely critical role in algebra. Linear algebra, they come up in lots of ways in modern algebra as well. And the short of it is a bijection is just a function that is both one-to-one and onto. It's an injective, surjective function, if you liked those French versions. If you have a bijection, you can now define a new object, the functional inverse. This is things we talked about in a pre-calculus course. But it's kind of nice to see how these all just sort of lace back together. The inverse is defined to go from the old codomain is now the new domain, and the new codomain was the old domain. So we're just literally flipping the direction of the mapping, and it has this property. If f inverse of b equals a, it just means f of a equals b. In other words, if you have the point AB is on the graph of f, then BA is on the graph of F inverse. And the inverse did make a showing in the notes already. So we won't do a whole lot with the bijection. The author's textbook in this concept here just pretty much mentions it. But there'll be a concept that we might come back to when we're later on in chapter 4. So just to think about this a little bit more, we're going to define a sine function and come up with a domain and range for which we have a bijection. But any questions at the moment with the definition? Okay, so we're trying to take f to map to from some domain into some range such that f is a bijection. But the expanded version of this is we're just looking for one-to-one and onto all at the same exact time. And one hint that came up in the notes a couple times is for thinking about a trig function like sine and cosine, the nice ones without all those vertical asymptotes, we have a great inequality. We can say -1. Let me get my colors back in action here. -1 is less than or equal to sine x, which is less than or equal to +1. These are all the possible outputs. So it's sensible to say the codomain should be -1 to 1. We want it to be the range at the same time because then that will give us onto. So that's a great starting point. Now we have to work on the domain. A trig function like this naturally has a domain R. But if we try to fit R into the domain slot, here's what it's going to look like from a graphing side of point of view on this. Here's sine x with no restrictions whatsoever. And we've got a big problem on this. It is still onto, that's not the issue, but this is absolutely not a one-to-one function. For example, the value of 0 gets picked up infinitely many times. At -pi as an input, it maps to 0. 0 as an input maps to 0, and so on, infinitely many values. Any integer multiple pi maps to 0 on the sine function. So in order to get one-to-one, we have to restrict this. Oh, didn't mean to do that, sorry. One sensible restriction is to say go from, how about the very bottom, because that picks us our lower element, -1, for the range. So if we say -1 less than or equals to x, less than or equals to, how about a +1? There's not much of a function left, but hey, that function happens to go from our very lower value, -1, to our very, hang on, let me look at that. X shouldn't be -1. Let me try again. How about -pi/2? That looks a little bit better. They go from -pi/2. Sorry, I forgot my trigonometry for a moment. we have the second coordinate output, a -1. So we do bottom out right there. And it is a bijection. So if I stopped at +1, it would work, but we want to make this domain as big as possible. So the sine inverse function, the actual inverse you get, is as useful as possible. So let's go all the way up to pi/2. That would do the job. We can't go beyond pi/2, add say +1 or any small value. And we have lost, let's go to 1 just so it's easy to see on the graph. We lose 1 to 1 if we go beyond pi/2, so we really have to stop there. And same if we go beyond -pi/2. So R doesn't work, but this set would do the job. In fact, we can make it slightly bigger by 1 point, and that's what we would usually take the sine inverse to be. So we would take F to go from -pi/2 up to +pi/2. So that's the domain and range that gives F as a bijection. So F is a bijection on this domain and range. And seeing it from the graphical side of this, here's what it would look like finally. Well, any last questions at all, folks, with 1-to-1 onto or the concept of the bijection? Okay, and this kind of idea works for just about any function. We've said a couple times that if you look into functions that look like this, x², well, this function is problematic, right? If you're thinking in terms of a bijection, it's onto if your domain is the non-negative numbers, but it's not 1-to-1. But change your codomain, say go from 0 less than or equals to x, and suddenly you have a 1-to-1 function. The inverse of this is just now the square root function itself. And we can see it's truly the square root function because there should be a reflection across y = x. But there's loads and loads of crazy topics we could get into with 1-to-1 onto the inverse functions, the bijections. But again, this is about where the textbook rounds off, just introducing this last topic. And to kind of wrap all these ideas together, that's the purpose of this table here. You can think of onto as just being the range's codomain. The formal definition will work more in the later chapters, is this one here we're citing in the notes. Same to 1-to-1 just means no collisions. And no collisions essentially just means this. If your inputs are different, your outputs better be different as well. And a bijection, the one we didn't have a lot of time to really get into, is meaning every single element in the domain pairs with 1 and exactly 1 output to the codomain. So there's nothing left off here, and everything maps exactly to 1 element inside here. Well, we did it, folks. That's the last topics on chapter 2.5 on functions. We're going to now move next into chapter 3, looking into logic. But any last questions or comments at the moment? Okay, again, thanks for the excellent questions and suggestions and getting through that unit. The next unit is probably going to be one of the funner units, I'd say, in this entire textbook. Sections 3.2, 3.3, 3.4 gets a little bit busy, but we'll work our way through it. This is where this becomes pretty exciting. Everything we've been doing before was just kind of setting the stage for this section here, 3.2. We don't have a lot of time to get too far into these notes. So let me just give you a kind of a guided tour, and then we'll give a look at example 1. Major things we're going to be doing in this unit is defining logical operators. The negation operator, the AND operator, and the OR operator, for example. We'll extend into exclusive OR, look into various things like truth tables, and we'll define things along the lines of the implication, like P implies Q. You might have seen me use this all over the place in the notes, starting on the first day of the course. We're going to formally define exactly what that means. This is one of the trickier ones. we'll define the biconditional, the if and only if. And then when we move into 3.3, we'll be looking into operations along with these bigger compound statements. But one really strong connection with what we've done already is, let's look at these three statements. Set theory. Out of nowhere, set theory and logic have a lot to do with each other. If you're thinking about the not operator, this is the negation of a statement, a proposition, but it's extremely analogous to the complement of a set. The complement of the set is all elements in the universe, not in a set A, and that not is the tie-in. It's not an element of. This one, the and operator, is saying P and Q. That's no different than the intersection. So if you're thinking that this and operator and intersection as being the same, and you're thinking of a logical and, it all ties in exactly the same way. So A intersect B means X is in a set A, and it's in the set B. So that's going to loop in with P and Q. And likewise, the union is going to loop in with P or Q. This one will be considered the inclusive or. So we're going to say formally exactly what we mean in terms of not, and versus or. And these are just the symbols that we'll write down on paper, much like the complement, intersection, and union. So that's a humongous analogy. If you take another look into these set theory operations, again, they weren't anything too major, but that's a really great refresher for what we're about to do in Unit 3.2. It all starts with, what do you mean by a proposition, really? And to fully define that, you have to wrap back to the very first part of the course where we introduced Boolean values. We didn't do much with it. We did like one small example, but Boolean values are making a tremendous comeback in the next 3 chapters, so we'll be mentioning them a lot. A Boolean value is either a true, and we'll often just write down T for the true as a shorthand, or as a false. We're going to look into Boolean valued functions, functions whose range is truths or false, just the 2 elements. It says Boolean values help us make decisions in code. We'll come back to that later on. And now here we define propositions. Propositions are the things we're going to connect with a or an and operator. It's a statement that is either true or false. Put in a quick statement here. It is not a statement that is a question. So it's not anything along the lines of a, what's the wording for that? I have a quick shorthand here. It is not a interrogative statement, which poses a question. I'm not very good at English, so not an interrogative statement. So a proposition, you can assign a Boolean, either a true or a false to it, and there is no middle ground whatsoever. It's either true or false, nothing in between. So for a particular proposition P, the truth value is the Boolean value, either T or F for short. So example 1 is just kind of a quick rundown to really internalize those definitions. It says determine which statements are proposition, and if it is a proposition, assign a Boolean value to it. So here's the first one. The integer 123 is prime. Prime means the only divisors for 123 is 123 and itself. So this is one of those problems where you might want to grab a calculator, take 123. There is one divisor I can see right away. It's definitely not 2, but 3 will divide that. Goes in 41 times. So the moment we found an integer divisor between 1 and 123, it means it's not prime. But it is a statement that's either true or false. Every single real number we mention, usually we're thinking domain of integers, any integer you put down, it's either prime or not. So we can say this is a proposition. It's either true or false. And this one evaluates to true. Hang on, let me try again. We found that 3 divides, it is not prime. This one evaluates to the Boolean value of false. 123 is composite. So that's our first proposition. We'll look into quite a lot of others when we're absorbing this material. But any questions at all, folks, with the part A? Okay, how about part B? Any volunteers to run through this one? Would you say it's a proposition or not? Yeah, exactly. It's false, absolutely, but this is an interrogative statement. It's a question. The answer to this is yes or no, really, not true or false. So if you see something like this, it's not the same as this kind of statement. A proposition is something that you would assign true or false to, but it's never a statement that's just a direct question. So if you see this one, this is like the trick problem in this entire section, really. This one is not a proposition. It is a question. I feel like that's extremely tricky. So you can convert this into a proposition by just saying 5 times 2 equals 4. Now it's a proposition. Because now it's turned into a statement that's either true or false. This one happens to be false. So watch out for the question marks. Any questions at all with that trick question there? Okay, the next one is, it's a statement as well. Z is a subset or equal to the set Q. The integers is contained in the set of rational numbers. This one is absolutely a proposition. What would you all say to this one? Is this true or false?
It's true.
Yeah, this one would be true. I mean, you could visualize, say, a number like 5. It's an integer inside of there, but you could rewrite that as 5 divided by 1. It's now in the form of a rational number. So yeah, this is a true subset relation. So we would say true on this one. So that's how we're going to be starting off the notes. 3.2 is going to be building off everything we do here. And then 3.3, we're going to define a predicate. That's going to be a proposition who depends on another value, say an integer or something else. But this is where we're going to start building on. From here, understanding what a proposition is, we'll move into the big 3 and then just start expanding our world to include implications, the if and only ifs, and so on. But any last questions at all, folks, with where we ended at today? Okay, well, this will be a pretty fun chapter. Again, it's really changing gears quite a bit. But you'll start to see as we go through the chapter, a lot of the stuff that we covered in chapter 2 does come back. So we're kind of planting the seeds for things that we needed later on. But have a great afternoon, folks. We'll be back to this next Tuesday.
Thank you.
Yep, take care.